Hi students, we're going to talk about position and velocity. So in our first example, it says, if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is s of t equals negative 16t squared plus 80t. So the first thing says, part A, find the average velocity over the interval from 0 to 2. So basically, they're asking for the slope. So when you see this is position, the original equation. So if I want velocity, it's the slope. And this goes back to our linear unit. All right, so the first thing I want to do is find my 2 points to do the slope of. So if I plug 0 in, my y value is 0. And if I plug 2 in for t, I get 96. So, slope, remember it's change in y over change in x, so 96 minus 0 over 2 minus 0, and we get 48. And that's feet per second. Okay, what is the instantaneous velocity at time t? So what is that asking for? That is asking for the slope at any time. So we're going to use the derivative. So I'm going to look and I want f derivative at t. So we're going to get negative 32t plus 80. So in other words, there we go, plus 80. So that's giving me the derivative or giving me the slope anytime I pick. Now what's the velocity at time 1? All I have to do is find the derivative at 1. We already have the derivative, so I'm just plugging in 1. And that should be 48. Feet per second. Okay, when is the velocity equal to 0? Well, I'm going to set my derivative equal to 0 and solve. So we subtract the 80. Oops. And divide by negative 32. And I get 2.5 seconds. Okay, I just rewrote the example at the top. We're on letter E. What is the ball's maximum height above the ground? Okay, so if we want the maximum height, we already know back here that at 2.5 seconds, the velocity is 0. And the velocity is 0 when you're not moving or you're turning. So think about it. The parabola is negative, so it's going to look like this. And I just found out when the slope equals 0. And the slope equals 0 right there. And that's at 2.5 seconds. So what I want to do is I want to know what is the height at 2.5 seconds. So we're going to go back to our original equation and find what it is at 2.5 seconds because we want the height, and the height is the position. So we're going to the position graph. So all I'm doing is plugging in 2.5 for t. So you're going to plug that in your calculator. You should get 100 feet. Because remember, we're looking for position. When does the ball hit the ground? Again, that's a position. So I want to set my equation, my position equation, equal to 0. And solve it. So I want to factor. Whenever you can factor, you want to factor. I can take out a negative 16 and a t. So I'm left with t minus 5. So if I solve it, I'm going to get t equals 0 and t equals 5. Well, when does it hit the ground? So think about it. I'm going to go back to my parabola that I drew over here. You're going to start here, okay? Your parabola is going to start. That was the 80 feet when I launched the ball. And then this is 5 seconds later when it hit the ground again. So my answer is going to be 5 seconds. For what values of t is the ball falling? Well, it's going to start falling. Remember, it's rising until you get to the middle, which is at 2.5 seconds. So it's falling. So we got 2.5 less than t is less than 5. So it's the points in between 2.5 and 5 seconds. And I didn't include 2.5 or 5 because the velocity at 2.5 and 5 is 0, so it's not falling. Okay, the last two questions we got. What is acceleration? So acceleration is beyond velocity, right? It's feet per second squared. So guess what? It's the second derivative. So if I went to my derivative, which was, let's see, let me go back a page, negative 32t plus 80, right? So negative 32t plus 80. I'm finding the derivative of that, which is just going to be negative 32. And it's feet per second squared. Okay? And then it says to graph the function, which I kind of did up here. That would be the sketch of my graph. And that would be 100 feet. Okay? So I'm going to have you guys try example 2. So take a look at example 2. You're going to try that example, and then we will go over it in class.